In this lecture, we're going to look at time series analysis, basically looking at signals and noise. Okay, and I'm not going to lie to you, I don't think this is the most exciting part of the course. However, it is very, very, very important because in many, many situations, not just in physics, but in the real world out there, people are often analysing signals and trying desperately to look for some kind of pattern or correlation in them. So astronomers, for instance, you're looking for a signal which is often very, very, very noisy, and you want to extract that signal from the noise, looking for some sort of correlations, and this is true in economics as well, and finance, and a whole lot of other areas outside of physics. So it would be a very, very brave scientist who claimed that time series analysis was completely unimportant. Okay. Also, there's a few bits of mathematical jargon here, but it's actually fairly simple and fairly straightforward. Okay, so let's get on with it. Okay, so we might have a series of measurements of some quantity x as a function of time. Okay, and in a lot of cases, x is a stochastic variable. It sort of varies quite randomly. And examples are shown below here. It could be the voltage here in a resistor versus time. So if you look at the voltage across a resistor, you'll find some signal which is varying quite randomly. It could be the position of a Brownian particle. It could be a stock price. It could be all kinds of things. Okay, and we're going to introduce this ensemble of functions x of t. Now you already know about ensembles, but x of t here is a member of an ensemble of functions for identical systems, each subject to random forces. So, for example, I could have a particle in a well. Okay, here's a particle, single one-dimensional well. Okay, I'll draw another one here. This is x, this is u, x, and you'd have one particle there, another particle in a completely identical well moving about. Okay, and you have many, many, many of these kinds of systems, and that will generate an ensemble. Now it's pretty clear that each of those particles is in some sense the same, but each of them will be doing a completely different random walk. Okay, and from that you can get a probability distribution of x of t. Okay, at each instant of time for x of t, there is a probability distribution w x of t, which tells us what the probability is for x at that time t. Okay, so we're going to use the abbreviation which is used in the textbook, which is we're going to abbreviate x1 t1 by this number 1. Okay, so thus we have w1x w11 dx1 is the probability that x has a value at time t between x1 and x1 plus dx1. So w is the probability distribution. Okay. Now, this W11 gives us the probability distribution for x at a particular time. Okay, but in many cases, we need to know more than this. We need to know time correlations, so we can define W11, W212, W3123, where the subscript labels the number of times we're including, and 1, 2, 3 here means x1, t1, x2, t2, x3, t3. So it means a triplet of pairs there. So, in general, wk, 1 to k, dx1, dx2, dxk, dx2, dx up to xk, is the probability that x has a value between x1 and x1 plus d1 at time t1, x2 at x2 plus dx2 at time t2, etc., etc., etc. Okay, so that's a joint probability distribution, if you like. Okay, it tells you lots of things. All right, now we'll introduce a very interesting concept, or very useful concept, shall we say, of stationary ensembles. Okay, they're ensembles such that the probability distribution is invariant under time translation. It's invariant in time. Okay, so W1 X1 T1 is independent of T1, so it's only a function of W1 X1. Okay. So let's go back to classical particle in a box, classical random particle in a box. Here's not a box, a potential I mean. Here's U, here's X. If I looked at the probability distribution for X, P of X, which we're going to label W1X, or X1, it's independent of time. Okay, if it's in equilibrium, then you know what W1x1 is. W1x1, we'll put the time 1 there as well, is proportional to x of minus u x1 on kt. You know that's a Boltzmann distribution. So you already know what that is, and that's stationary. It's independent of time. Okay, so let's run out some of the stuff here. Okay, and what more can we say here? Well, if we have more than one variable there, or more than one time, suppose we have several times, Wk depends only on the time differences between the different times, not on the absolute value of the times. Okay, so it doesn't depend upon where you started, but it depends on where the difference in times between x1 and x2 when you're measuring x1 and x2. Okay, for a Brownian particle in a potential, as I said before, we have this distribution here, and it's independent of T1. Okay, and if I have, say, a probability distribution with 2 times in it, it depends only on T2 minus T1 and not on these two things separately. Okay, so to make that more explicit, the probability of finding the particle at x2 at time T2, if it is started at x1 at time T1, does not depend on T1, merely on the amount of time it had to get from x1 to x2, not on the time when it started, and that time is just T2 minus T1. Okay. Now we're going to talk about the average, and of course the average, you already know how to get averages. Okay, if we want the average value of x of t, we just average over all x1 from minus infinity to infinity of x1 times the probability distribution divided by the normalization factor. And the normalization factor should be 1, and so that should equal 1. So the probability, the average value now of x of t is given by that. Okay, now we've gone away from stationary distribution, so we've put back in here the t dependence. Okay, if we have a stationary ensemble, then w1x1t is independent of time, and hence so is x. It's no longer a function of time. Okay, in a stationary ensemble, the ensemble average is the same as the time average. So here's the time average here, on this side here, and the ensemble average is basically the same thing as that. So the fraction of heads in a coin toss is the same if we toss one coin many times or many coins once. Okay, that's the average, and you already know about averages, so I don't think there's anything exciting there. All right, in some earlier quizzes, probably very early in the course, we met correlation functions, and these are quite confusing when you first meet them, but as you go on in time, you get it becomes simpler and simpler. So in many cases, we're not merely interested in the average value of x, but how x of t behaves at 2 different times, t1 and t2, say. Okay, we thus introduce a correlation function. This is the correlation function on the left. That's the symbol we use, and this is how it's defined. Okay, you can see it's got the probability distribution function for x1 at t1 and x2 at t2. In other words, this is the probability distribution at t1 that x will equal x1, and at t2 x will equal x2, and integrating over x1 multiplied by x1, x2, and you get the correlation function. You can see it looks very similar to the average, except it's got 2 x's in it. Okay, the one there. Okay, so it's got x's at different times. In a stationary ensemble, this can only depend, this thing here, this correlation function can only depend on t2 minus t1. Okay, so that must mean we're able to write it like this. We've got x naught, we can put the first one at 0 if we wanted to, x of t, okay, and then we write it like this because we've only got one function here. Okay, we could have chosen any variable here. We could have chosen tau and tau here, and this would be x plus tau. Plus tau there. Okay, but we won't do that. Okay, let's get rid of that. Okay, so we also define higher order correlation functions if we wanted to. You can imagine extending this kind of thing to 3 variables, 4 variables, etc., etc., etc. Okay, they tend to be less useful, but you can still define them. In statistical physics, and particularly in condensed matter physics, we also define often spatial correlations. So the density of particles, for instance, rho of x, we can define a correlation function like that. which tells us how the particles interact. Okay, oh, and there's a nice picture by Renoir, just to take a break from all the equations we're showing. All right, so the Fourier decomposition. Now you already know about this. Fourier transforms. If you have a time series x of t, you can write the Fourier transform of that just by multiplying by e to the I omega t and integrating from minus infinity to infinity, and you get the Fourier transform of the average. Okay, and we happen to know, of course, that x of minus omega is x star of omega, where star means complex conjugate, because x of t is real normally in these situations. So if x of t is real, that's certainly true. The inverse transform you get by replacing the plus I by minus I and dividing by 2 pi. And that gives you the inverse of the average. So here's the Fourier transform of the average. Here's the actual average itself. Okay, the average value x at some time t. Okay, of course, this notation implicitly assumes you're not in a stationary ensemble. If you're in a stationary ensemble, you would replace that just by x, because there'd only be one average. Okay, now, of course, we can also do the Fourier transform of the correlation function. Now, to do the Fourier transform of that, you just take your correlation function here, which we know, and you multiply it by 2 exponentials with 2 frequencies, omega 1 and omega 2, and you integrate over 2 different times. So you can compare that with this one here. We've done one integration over time here. Here we've got 2 integrations over time. Okay, and we can also, of course, then invert that and get this equation here with some minus i's and some 2 pi's. Okay. Now, if we had a stationary ensemble, this we can simplify a bit further, this correlation function, because T1 would then be equal to T, big T, minus tau 2, and T2 would be equal to big T plus tau 2, where T here is the absolute time, and tau is the difference from the 2 times. Okay, so we can write this expression here, this bit, as omega 1 T1 plus omega 2 T2 is omega 1 plus omega 2 big T plus omega T minus omega 1 tau 2. Okay, so this is the absolute time, this is the difference in times between the two situations. Okay, so if we have a stationary ensemble, then we can demand that depends only on the time difference and not on this thing, the absolute time. Okay, so if we did that, we can write out our expression like this. We haven't done anything here. In the textbook, they've missed out the double integral for some reason. You can write our correlation function looking like this. And if we have something which is independent of T, big T, which is true for a stationary ensemble, then this thing here must be 0, except when omega 1 plus omega 2 is 0. So basically we've got to get rid of this term somehow. And the only way to get rid of it is to have this 0 except possibly where omega 1 plus omega 2 is 0, in which case T just drops out anyway. Okay. So if you do that, then you must have x omega 1, x omega 2, the Fourier transform of the correlation function, equal to 2 pi times s omega 1, where s is just a function of omega 1 plus multiplied by a delta function, which enforces this rule here. Okay, and this thing s is called the power spectrum. Okay, and it turns out that s of omega is equal to s of minus omega. You can prove that to yourself. Okay, so that's the power spectrum. If you have a stationary ensemble, you can define things like that. So, what does the power spectrum mean? Okay, it measures the strength of the different Fourier components. So it measures how much of this frequency you have as opposed to that frequency. Okay, if we have white noise, then s of omega is independent of omega. Okay, so white noise implies we have a very flat spectrum as far as the power spectrum goes. This S omega is flat. All the frequencies have equal weight. So white noise means all the frequencies have equal weight. Okay. So getting away from white noise again, let's go back to the ordinary power spectrum. If we put the power spectrum back into our equation over here for x1, x2, okay, we take that and we put it up into there. What we find is this equation here. Okay, that should be a minus there, minus it. That's our expression for the correlation function, or we can write it like this in terms of cosines. We've used the fact that S of omega is S of minus omega. Okay? So what we've shown now is the correlation function is the cosine transform of the power spectrum. Okay. So far, in fact, we haven't done much in the way of physics. If you look back here, it's just a whole lot of definitions of things. There isn't any real physics here. I mean, sort of just definitions of Fourier transforms and things, and definitions of what power spectrum is. Okay. Right. So this leads us to the Wiener-Kinchin theorem, which is basically that you can invert this S of omega and get the following expression for S of omega in terms of the correlation function, which you could also write, if you wanted to, just in terms of integrals over, it should be a integral here over dt, okay, of the correlation function. Okay, you integrate from 0 to infinity only over the positive times. Okay, so what it says is the power spectrum and the correlation functions are cosine transforms of each other. So if you know the power spectrum, you know the correlation function, and vice versa. And that's the Wiener-Kinchin theorem. And put another way, if we know how the power is distributed with frequency in the system, we know how the system is time correlated. So the distribution of power with frequency tells us something about how the system is behaving with itself with time. Okay, and this result was derived by Norbert Wiener in the US in about 1930, and Alexander Khinchin in the USSR in about 1934. But in fact, Albert Einstein had already derived it in 1914 and kept the note in his desk. Okay, so it's a fairly fundamental theorem, although Einstein didn't feel like publishing it at the time. Right, so that's the Wiener-Kinchin theorem. It just relates the correlation functions to the power spectrum. So what I haven't defined for you is, or not described at least, why is this thing called the power spectrum? Okay, that wasn't made clear. So we have that this is true. Okay, and if we go back here, yeah, that's what we get. Okay, let's put t equals 0. Okay, that means x of 0, x of 0. Okay, x of 0 is the same thing as x squared, the average value of x squared, which would look like that, putting t equals 0, which will just give us that. Okay, which is very simple. It says that the average value of x squared is the integral over all positive frequencies of S of omega, apart from a factor of pi. Okay, so let's think of the following scenario. If we have a resistor, 1 ohm, okay, and we measure the current in it. So there's a current I. Okay, the power in that resistor is I squared R, which is just I squared. Okay, so if we replace here x squared by I squared, that's basically the power in our resistor. Okay, and this thing on the right, the integral over S of omega, over omega of S of omega, just looks like the power per frequency range. So S of omega divided by pi is basically the power per frequency range, and that's why it's called the power spectrum. Okay, so it's actually related to the power. Somehow x squared should be the power in some cases, and that's why it's called this. Another bit of art, this one's in the Art Gallery New South Wales, which of course is closed at the moment, but you can go and see it when it reopens. It's a very nice picture. Right, now, so much for power spectra and the Wiener-Kinchin theorem. let's look at extracting signals and noise. Okay. So how do we define noise? Well, you can define noise how you like, but we're going to define it as something where all of its Fourier components are stochastic variables with zero mean. Okay. Anything else is a signal. But if all of your Fourier components have a stochastic mean of zero, then you're noise. Okay. A signal, which is not like that, a signal is something that has a definite periodic component. Okay. If x of t has no periodic components, then the correlation function will approach zero as time approaches zero. Okay. So the simplest kind of decay is exponential. So let us assume we have a correlation function which looks like this. It decays away in time. Okay, so you're saying how is x of t related to x of 0? Well, if t is 0, it's strongly correlated. You've got c there. But if t goes off to infinity, you get nothing. There's no correlation. Okay. If you take the cosine transform of this particular function, the exponential one, you get a power spectrum which looks like that. And you should try and do that yourself. Go away and do it. Stop the video. Go away and make sure you get that result. Okay, Huang gets a different result, which leaves off the C or something, I can't remember. Probably leaves off a gamma. All right, so that distribution here is called Lorentzian. It's given a special name because it occurs so often. And it looks a bit like this. So if I have g of t, a correlation function is decaying exponentially, then our power spectra looks like this function here. It looks like that. Okay, so if we have our original correlation function looking like that one, the exponential decay, white noise would correspond to gamma goes to infinity. In other words, it would correspond to this decay being decaying in zero time. Okay, and in that case, you would find that the power spectrum looks flat. Looks like this. Okay, that's what the power spectrum would look like. All right, so if you take the limit as gamma goes to infinity, you will see that this thing becomes something like a constant. Okay, it's actually zero eventually, but it's a constant. Okay. All right, now let's take a system which has some signal and some noise. Okay, because a signal which just has noise is probably not particularly interesting, and if your signal contains only noise, you're probably wondering why you're doing the experiment. Okay, so suppose we have a noise term y of t such that we get this. Okay, this is our noise correlation, which is going from x to y. Okay, but we also have a periodic component like this. This is our signal. It's a nice cosine function. Okay, and we're going to take our total signal to be the noisy bit plus the other bit. Okay, so we've got a bit that's going crazy and a bit that's going like this. Okay, if we do that, we find a correlation function that looks like this. Okay, you can take that and find the correlation function, which is that. I suggest you go away and do that. And then you can find the power spectrum, which turns out to be a nice Lorentzian, plus another term which is a delta function at omega 0, where omega 0 is the frequency of our signal. Okay, so then we get a very nice Lorentzian plus a delta function telling us where our signal is. Okay, and so here's our signal and noise. Here's the power spectrum, and here's here's some graphs of different kinds of signals here. So here we've got something which has a DC signal. It has an AC signal here, and it has some noisy bit as well. Okay, and when you do that, what you find is the DC signal gives you a spike in the power spectrum at the origin, as it should. It's got zero frequency. The AC signal gives you a spike at whatever frequency it's acting at, and the rest of it gives you this background Lorentzian kind of stuff. Okay, and that's where we will end that particular lecture.